Good morning, everyone. My name is Suyani, and I'm a first year PhD student from Zhangjiang University. This is my first time attending an international conference. I feel a little nervous, so I have prepared a lot of text in my PPT in case I can't remember what I want to do. Sorry about that. If I keep looking at the screen, maybe I can remember what I want to do. My main contribution is in the implementation of generative AI algorithms. I'm not very familiar with optical networks. Unfortunately, our main contributor for it is unable to attend. I'm sorry if there are any inaccurate statement. So it's a good opportunity to introduce our OpticGAI generative AI deep reinforcement learning for optics networks optimization. Deep reinforcement learning OpticGAI is considered a promising tool for optimizing optical networks. However, the flexibility and the efficiency of current DR-based solutions still need improvement. Generative AI or GAI has shown significant performance advantages across various domains, mainly because of its great method feature extraction ability. So the natural idea is to explore the GAI in our policy design paradigm for optical networks. The generative models like different models or large language models have shown remarkable performance. It's clear that generative AI will profoundly impact many AI-related domains, including automated network optimization. On the other hand, DRL has recently gained widespread attention as a promising method for solving communication network problems. The most common use is to use the DRL agents learn the heuristic algorithm for sequential decision-making tasks. However, this approach still faces challenges such as requiring excessive computing resources and needing more flexible policy design. By combining the strengths of generative models and DL, we can create more efficient and we try to create more efficient and flexible solutions for optical network optimization. Recent research has explored using DR for optical network optimization. So the DR agents can optimize linked loads by learning ways of develop heuristic algorithms for dynamic routing, modulation, and spectrum allocation or RMSA, as well as static routing and wavelength assignments, RWA. Additionally, advanced DR algorithms like advantage actor critic A2C, asynchronous advantage actor critic A3C, and multi-agent reinforcement learning are being tested for various optimization tasks in optical networks. And so researchers have been working on fast and scalable resource allocation algorithm for the tough for the anti-hard program like RWA. There's still a big need for new solutions. Recent advances in DR show great promise for improving network operations. DR has used to enhance algorithms for both dynamic and static routing challenges, like the RMSA and RWA. For example, like I said before, the DRL techniques have optimized the OSPF with two-way to handle link loads more efficiently. Some algorithms have been developed for RMSA, addressing issues with sparse reverse, something like this. Researchers have also explored various DRL algorithms, which this work, our work mainly focuses that this algorithm, for instance, DQN combined with graph neural networks helps optimize routing in optic networks. The A2C and the A3C methods are used to improve algorithm for service provisioning and RMSA in elastic optical networks. Meanwhile, the multi-agent RL tackles complex inter-domain RMSA tasks, showing how distributed problem solving can be effective. However, currently, this current method for the optic network optimization face several challenges. First, this struggle with wavelength alignment, scattering, and path selection. Second, the complex topologies of optical networks make it hard for DRL to make accurate decisions. Third, DRL methods need to quickly adapt to dynamic changes in network traffic. These issues arise because fixed neural network structures have difficulty learning from diverse network conditions. As a result, DRL often generates unimodal policies, leading to local optimal and limited adaptability. Generative models, however, excel at capturing complex distributions, so we are exploring whether the GAI technology or the AIGC technology can enhance the flexibility and the performance of DRL-based optimization algorithm. In this paper, we introduce OpticGAI, the AI generative policy design paradigm for optical networks. In detail, it is implemented as a novel DRL framework that utilizes generative models to learn the optimal policy network. We assess the performance on the two classic programs, RWA and RMSA, to show the feasibility. Here's how it is implemented. We introduce in this paper we introduce the diffusion supported policy optimization paradigm. This means we integrate the diffusion model with network data to handle complex relationships between stakeholders and decisions and adapt to dynamic environments. We use the Noisome diffusion probability model (DDPM) for survey select for the policy network in our model. Let's see the picture. The diffusion supported policy optimization paradigm is illustrated in the figure. The diffusion model is used as a policy network in the DRL algorithm to balance exploration and exploitation. The diffusion model captures the mapping between states and decisions to generate optimization actions for optical networks. The reverse process of the DDPM is adopted as a policy. The reverse process of the DDPM is adopted as a policy network. This policy network samples noise from the Gaussian distribution and predicts the noise to be removed at each denoise step based on state and the previous action. After T denoise states, the final optimization scheme for the network is generated. The diffusion model works by learning to clean up random noise and uses multiple steps to create the content from it. In the context of when the diffusion model acts like a policy network, it takes the network and the service states as inputs. As mentioned before, we use the DDPM to explain how these models function as policy networks. The DDPM has two main processes: diffusion, the forward diffusion, and the reverse generation or denoising process. The diffusion process adds Gaussian noise to the essential spin A0 from distribution over T steps, gradually tuning A0 into Gaussian noise AT. On the flip side, the denoising process takes the Gaussian noise and perform T steps to clean it up, eventually removing the added noise to restore the original data. So it's a generative method. For the optical network optimization problems such as RWA, we focus on reverse process of the DPM. Firstly, the policy network samples noise from the Gaussian distribution. Then the noise prediction network predicts the noise to be removed based on its on the state and the output action from the previous time step. After performing denoising options over T steps, the scheme of optical network programs is generated. In addition to policy networks, effective state representation and action space are crucial for the learning process. Taking the RWA as an example, our goal is to use a chain agent as a specific network input represented by giving traffic metrics to create a specialized heuristic method. This method will output fitable solutions. The static RWA program can be formulated as an integral linear programming problem with the perspective of maximizing network performance. And then to reference an RWA program instance with uniform traffic distribution. In each event, the agent decides to accept or reject a connection request based on its observations. At the end of the episode, resources are reset and a new traffic metric is processed. The observation space of OpticGAI includes the source destination pair of the current request and the spectrum's occupancy of the key shortest passes forming a vector. In each training iteration, OpticGAI collects transformations from interactions. These transformations are sampled in subsequent iterations to update the critical and policy network parameters, driving the optimization algorithm. For the RMSA, we mentioned consistency with previous work. The paradigm involves a remote SDN controller interacting with local SDN agents to gather network state and lattice requests and distribute the RMSA solutions. Upon receiving a request, the controller retrieves key network states representations, including active light passes, resource utilization, and topology to generate the state. The OpticGAI policy network processes this state and outputs the RMSA policy. The controller acts on the policy by attempting to establish the corresponding light path. The environment provides feedback and immediate reward. The objective is to maximize long-term community rewards while servicing requests, allowing OpticGAI to learn adaptable RMSA policies through dynamic light path provisioning. Then in this section, we evaluate the performance on the representative of the optical network the optimization problems. As proof of concept experiments, we conducted experiments on RWA and RMSA. For the RWA program, we want to create a heuristic method for the program that can handle wavelength continuity constraint and come up with feasible solutions from a given flow matrix. To start, we evaluate OpticGAI on the static RWA program of a 10-node optical network space. We use two versions of the PPO algorithm as our baseline. We also use LP for the optimal solution and compare OpticGAI against the heuristic algorithm like shortest path fitting SP, PSP, and least loaded path LP. Plus, we include the optimality bounds of IRP as part of our baseline evaluation. And so we evaluate the blocking rates of OpticGAI advanced PPO heuristic algorithms and IRP on 500 static matrix of RWA tasks. Now the blocking rate is a critical performance metric in optic in our task, indicating the proportion of connection requests that can't be accommodated due to resource limitations. We can see from the figure OpticGAI really achieve the lowest blocking rate, which means it's doing a great job at optimizing the use of optical network resources. The PPO variants show the varying degrees of effectiveness. Specifically, PPO-MS, the multi-stop version, and the PPO-4 perform better than PPO-FF first fit. On the other hand, heuristic algorithms like SP and PSP have their blocking rates suggesting they are less efficient where it comes to allocating wavelengths. IRP performs pretty well. It's still not, but it's still not as effective as OpticGAI. While IRP shows effectiveness with a low blocking rate is lack of scalability due to the limited nature of the RWA program limits, which limits is practical application. Okay, so in elastic optical networks, the RMSA task is a big deal. We said that each fiber link can handle 100 of frequency source. When it comes to service requests, we assume they follow a Poisson distribution with a uniform traffic pattern. The required bandwidth for each request is evenly spread. On average, services arrive every. This is some detailed setting. For the RMSA program, we compare the OpticGAI method with 4 advanced DIR method to demonstrate its performance. We use the algorithm provided by the stable baseline for implementation, and the parameter setting follows established guidelines. The neural network we use has 4 layers. All the other parameters are set at their default values. So to maintain consistency, the experiment is conducted on the NSFNet topology following the guidelines. Under the same modulation format and other settings, as you can see in the figure, the OpticGAI is the first model to hit the reward of 40, and it's also the only model that achieves a reward value of 42 or more. Compared to other models, it maintains a slight advantage. Notably, the DQI is a worse performing model, and because of longer time to converge, at the same time, PPO slightly up from the HC. So this figure further illustrates the performance of this algorithm in the terms of blocking rate. We can conclude that error rewards mean lower blocking rates. Okay, consistent with the results in the last figure, OpticGAI achieves a better blocking rate right from the start of training. So this work takes a different model-based policy network as a case study to show the capability of OpticGAI. It's a kind of preliminary work. Beyond the different models, other generative models like large language models have also been extensively validated for their robust generative capabilities. Given this backdrop, indicating other advanced generative models into the framework holds significant promise for enhancing performance in network optimization tasks. However, the motivation behind this integration and the specific implementation warrants further elaboration and exploration. First, technically speaking, can all types of generative models be effectively incorporated into network optimization? Second, what tangible benefits does the introduction of generative models bring to real-world network optimization scenarios? So generalization capabilities are also a pivotal concern in deploying generative AI AGI systems in optical networks. These systems must demonstrate robustness not only across different traffic metrics, which can fluctuate significantly in volume and cadence, but also across diverse network topologies that range from simple to complex configurations. Addressing these challenges requires robust testing and probably the development of more sophisticated training methodologies. And the complexity of AI methods, especially when augmented by generative models, often result in a black box nature, where the decision-making processes are not so very opaque and difficult to interpret. This lack of transparation this slide can be a significant barrier, particularly in critical systems like optical networks, where stakeholders really need clear and comprehensible explanation of how decisions are made. Explainability ensures that the decisions made by complex models can be understood, thereby increasing confidence in the stability of communication systems. And so, in conclusion, OpticGAI is a promising AI-generated policy paradigm in optical network optimization. which effectively handle resource constraint and multi-type complex optical network tasks. It allows for the automated generation of policy decision models without the need for pre-designed network structures. This work exploits the feasibility and advantages of OpticGAI paradigm in resource constraint and multi-type optical network tasks. For future work, we'll focus on designing more universal IDC and enhanced policy design to obtain more flexible and efficient solutions. Okay, we have some Xiaolong from Polytechnical di Milano from his questions. Thank you for your attention and for giving me the opportunity to share our work today.
Okay. Well, since the time is limited, only one question. So for the evaluation, how much time you run ILP for each topology? How much time you run the ILP to get a solution? How long you run to get the optimal result? How long it takes?
Sorry, I don't do this. It's just I think it's a current website. There is a current website for this problem. Okay. It's not our work to implement this software.
Okay, thank you. Okay, let's Siya again.
Okay, so that's the end for the morning sessions. Please go to the lunch and come back at 1:30. Our afternoon sessions start at 1:30.